Okay, Year 11. In this lesson, we're going to look at proofs by contradiction. And I've gone back to our header page from the last lesson and the three proof types that we're going to, or methods that we're going to be exploring. Yesterday was about the direct method, just using, proceeding and trying to find that, find that left-hand side and right-hand side matched up, or we got to our end goal. Now, today we're going to look at another method, which is, I guess, slightly counterintuitive, or slightly strange, or be certainly different to any type of mathematical procedure that you've perhaps done in the past. In that we're going to assume false. We're going to proceed along logical lines with the view to hopefully finding out that we will come across some kind of breakdown in the logic. We'll come across a contradiction in our logic, and we'll come up against something that we know to be false. And so therefore we can go back and say, well, it must therefore be true. It's a kind of convoluted method of proof, but it does come in handy. It does come in handy for some properties, or some proofs that need to be made. Sometimes contradiction works in that you can just go, right, well, let's just say it's false, and show that just turns into a load of nonsense. So that's today's. It's proof by contradiction, and so we'll get that title up. So I guess the steps involved here. One, we're going to assume that whatever statement is being offered, we're going to assume it's false. So we're playing a game here. Two, we're then going to use logic, all right, or axioms, or formulae or theorems to arrive at a contradiction. All right, it's going to break down somewhere, and it's going to be a block, and so we're going to go back and say, well, the assumption must have been wrong. And so that's what our third step is to acknowledge that the original statement must be correct. The original statement must be true. Okay, so how does this work? Let's look at an example. Okay, so in the first example, we're asked to prove by contradiction that if the integer n is odd, and odd to us means the integer n, so we'll use some other pronumeral, then odd is represented by 2p plus 1, then the square of n is also odd. Now, if this didn't say prove by contradiction, all right, if that wasn't there, if it just said prove that if the integer n is odd, then n squared is also odd, you would just proceed and say, okay, well, n is equal to 2p plus 1. And therefore the square of n is 4p squared plus, I'm sure we did some of these in the last exercise, which is twice p squared plus, 2p squared plus 2p plus 1, which is 2 times some integer m plus 1, which is odd. All right, and that's what we do. That's the proof done. We are asked here to prove by contradiction, so we have no choice. We have to use this method. So the next example we do will be one where is the most famous contradictive proof there is, and the reason for that is that you kind of have to use contradiction to prove it. But this particular proof is much easier done in a direct way. But we're going to go indirect. We're going to find a contradiction. So in order to do that, we're just going to practice this out. We're going to assume the statement's false. So step one, we're going to assume that n squared is even. Right, now if that's the opposite of odd, right? So assume n squared is even, therefore that when n is odd, n times n is going to be even. It's going to give us some value of 2 times something, right? So k is an integer. So this is what happens if we assume n squared is even, that we've got this situation happening. But we know that n is an odd number, so we say, but since n is odd, n times n is also odd. So it's broken down. We can't get n times n to equal 2k. It's broken down already. So we are already there at a contradiction. So therefore, n squared must be odd. And there's our proof. Let's have a look at another one. This is a more classic example. Example 2. Prove, I'm not going to say by contradiction because in this case there is really no other method. Prove that the square root of 2 is irrational. Okay, so you know that an irrational number, rational numbers are defined by, or can be written p over q, where p and q are integers, assumed to be relatively prime in simplest form. That's what defines a rational number, a number that can be written as a fraction. So irrational numbers can't be written in this way, and so our proof our first step is to assume that root 2 is rational. So that's what we're going to do. We're going to say assume square root of 2 is rational. All right, because what we know is that square root of 2 is actually irrational, like pi, like e. It's going to go on forever as a decimal, as a decimal that doesn't have any pattern to it. It can't be written as a fraction. It's an irrational number. But we're going to assume it's rational, and this thing's and we're going to show how this thing breaks down. So assume root 2 is rational. Well, what that means is therefore root 2 is equal to some m over n, where m and n are integers and are coprime. So that means there's no common factors. So it's in simplest form. Okay. So if this is the case, then let's go. So what would we do? We could just square both sides. So we could get 2 is equal to m squared over n squared. Okay, well, if that's the case, then m squared would equal to n squared. And therefore, you'd say that m squared is even. And if m squared is even, m's even. Therefore, m is even. And we could deduce that m is equal to 2 times some k, where k is an integer. Okay, so m's even. M is equal to 2k. Well, if m's equal to 2k, we could therefore say that m squared now becomes 2k squared. So some even number squared is equal to 2n squared. So that would give us 4k squared. And that would give us that n squared is equal to 2k squared. And now n's even also. So therefore n's even. Now we've got n is even and we've got m is even. Let's go back to our assumption that root 2 is m over n, where m and n are integers and are coprime. How can they be coprime if they're even over even? We've got a common factor of 2. So therefore m over n can be simplified, right? Because we know that at least 2 is a common factor. So therefore, the assumption is false. Assumption is false, and therefore root 2 is, in fact, irrational. So that's a very famous proof. It's an interesting one. We're being asked to prove something that we know is the case, but then, you know, in mathematics, it's a great thing that you can prove things. Like I said, maths proofs, once they've been established, cannot be refuted. They cannot be challenged. And when you prove something, you establish it for life. And it almost gives you a license to go ahead and use. And that's why whenever we can in this course, we will prove things. We will start from first principles, start from basic first principle logic, and build steps to come up with proofs that we have some ownership over once we've proved. I think if we just use things that other people have proved, we're really no more than machines. So that's the difference, I think, between a mathematics student or a mathematician and just a machine. So this is really good. This is going to be a good week where we're going to prove things, and we're going to do it throughout the course. Okay, let's have a look at another example. Okay, here's an interesting one. Here's prove that there is no x in the real number system. So there's no solution x such that 1 over x minus 2 equals 1 minus x. There's no real solution to this. So we're going to prove by contradiction. So we're going to assume that x equals a solves 1 over x minus 2 equals 1 minus x, where x is a real number. Let's just go ahead and do that. So if this is the case, off we go. 1 over, so I can put a in here and I will get a solution. So if that's the case, I've got 1 equaling 1 minus a by a minus 2. Therefore, we've got a minus 2 minus a squared plus 2a. So therefore, a squared, what have we got here? We've got minus 3a plus 3 will be equal to 0. And so therefore, a is equal to 3 plus or minus the square root of b squared, which is 9, minus 4ac over 2a. So a is equal to 3 plus or minus the square root of negative 3 over 2. So hold on a second. We're told that x is a real number, but x is clearly not a real number. So therefore, a is not a real number. So therefore, false. So therefore, there exists no x in R such that 1 over x minus 2 equals 1 minus x. 1 over x minus 2 is equal to 1 minus x. Okay, next example. Okay, so prove that if m and n are integers, then m squared minus 4n minus 7 is not equal to 0. Okay, so look, with these examples, it'd be really good for you to, as you gain in confidence, maybe have a crack at them, you know, just try and get ahead. You're getting about 20% out of these if you're just watching. You'll get way more if you are contributing, if you're testing yourself. Even if you get it wrong, you're pushing, and that's fine. You can press play again anytime, but see if you can get ahead. See if you can do something with this. Okay, first, I mean, even if all you do is just write out the first step and just start it, have a go. Okay, so we're going to assume, and we always just start with that word, assume it's false. Presume that if, so assume that m squared minus 4n minus 7, m squared minus 4n minus 7 is equal to 0. Let's just assume that. So if that is the case, that there is some for mn integers, then right. So therefore, if that were the case, then m squared, we've got to fly into this, you know, and just see where the absurdity comes up. 4n plus 7, right? So m squared is now 4n plus 7. So what does that mean? And hopefully we're picking up that these things, we're looking for odds and evens, and they're key components to these. So if m squared, like 4n plus 7 is odd, because 4n is even, and we're adding even and odd. So therefore you can say that m squared is odd, and if m squared is odd, then m. All right, if m squared is odd, then m is odd. And the thing is, once we've established that something is odd, we say, oh, let's write it as an odd number might look, 2k plus 1. Okay, so now we go back to the start and say, okay, therefore, let's say that 2k plus 1 squared, so I'm now back up here to my assumption, minus 4n minus 7 is equal to 0. Let's see how this looks. So this is 4k squared plus 4k plus 1 minus 4n minus 7 equals 0. What's going on with this? I can see 4 is a common here, so I might even pull that out, say 4 outside of k squared plus k minus n, and I might get the 1 minus, I'll get 6 over this side, so I'm going to divide through by 2 to get twice k squared, plus k minus n is equal to 3. Oh, that's interesting. Now what's k? K is, up here I should have said k is an integer. K is an integer, n is an integer. So this is an integer, twice integer, so this has to be even. Left hand side is even, right hand side is odd. Left hand side equals even, right hand side equals odd. So it's broken down. So therefore, false assumption. So therefore, the original statement is true. Therefore, m squared minus 4n minus 7 cannot equal 0. m squared minus 4n minus 7 cannot equal 0 for m and n as integers. And finally, just some counterexamples. You've only got to find one. And so just a couple of examples here. If n squared is divisible by 4, so is n. Okay, so this is a claim. Show that this statement is not true. So all we've got to do is find, we've either got to prove it's true, or we've got to find one example of it not being true. That's all it's going to take, one counterexample. So if n squared is divisible by 4, so is n. So let's think about what's multiple of 4 that's a square. So maybe 16. 16 is divisible by 4. 4 squared is divisible by 4. So is 4. Well, that's actually true. So 4 squared is not a counterexample. In fact, that just supports it. N equals 4 is good. What about n equals 5, 6? Yes, that's divisible by 4. N equals 6. So we get n squared. So we get n squared is equal to 36. That's divisible by 4. All right, because that's equal to 4 times 9. But then n is equal to 6, which is not divisible by 4. All right, and an easier way of writing that is probably not equal to 4k, where k is an integer. So therefore, statement false. Statement false by counterexample. Okay, if n squared plus 1 is a prime number, that's a big statement. We've only got to find one where it's not. Doesn't take long. 1 squared plus 1, that's prime. 2 squared plus 1 is 5. 3 squared plus 1, n equals 3. We get n squared plus 1 is equal to 10, which is not prime. Therefore, n squared plus 1 is not a prime number, is not always a prime number. So you can't make the statement that n squared plus 1 is a prime number. By counterexample, that's done. Okay, I think we need to get some practice at this. It's exercise 1F, and that's your work for this second unit of week 3.